Passage 6. Flameless ration heaters are used by combat soldiers to heat their meals in the field. Oh, sweet. The heat is produced when magnesium reacts with water. And here's the, so, I'm not going to look at all of it, but there's the middle point where the reaction occurs. The rate of the reaction increases in the presence of iron and sodium chloride. So those are probably like catalysts or enzymes maybe. The following experiments were done to determine how to design FRHs. All right, cool. A 1 mole piece of magnesium ribbon. Okay, let's put this over here too. Magnesium. 0.10 mole of iron powder and 0.10 moles of sodium chloride were added to 25 milliliters of H2O at 20 degrees Celsius in an insulated container. So the heat's going to stay in there. The mixture was stirred constantly and its temperature was measured every 50 seconds. The experiment was repeated with magnesium ribbon cut into 100 pieces and magnesium powder. Okay, so what's changing here, I want to think about, is the surface area of the magnesium. Whoops. That's exposed into the reaction. So the ribbon has the lowest amount of surface area, and then the cut ribbon has more surface area, and the powder has even more surface area. And I'm going to write on here, so this is powder, and this is ribbon, yep, and this is, oh, this is cut ribbon, and this is just plain old ribbon. Okay, and as I would expect that it got hotter faster the more surface area was available. All right, experiment 2. Powdered magnesium, 0.10 moles, was mixed with 0.1 mole of sodium chloride. The mixture was added to 100 milliliters of H2O at 20 degrees Celsius in an insulated container. The mixture was stirred constantly, and the maximum temperature increase that occurred within 15 minutes was recorded. The procedure was repeated with different amounts of iron powder added to each mixture. See Table 1. Okay. Okay, so they started with no iron at all, and then they started adding iron. So that's what we're looking at here. The key is iron. And experiment 3. Powdered magnesium, 0.1 mole, was mixed with 0.5 moles of iron powder and added to 100 milliliters of blah, blah, blah in an insulated container. The mixture was stirred constantly, and the maximum temperature increase that occurred within 15 minutes was recorded. The procedure was repeated with different amounts of NaCl. Okay, so again, this is varying the NaCl. Okay. Question 30. Which of the following is the most likely reason that amounts greater, okay, experiment 3, than 0.125 moles of NaCl were not tested in experiment 3? Okay, so at 0.125 centimeters, the temperature increase was 82 degrees Celsius, and the solution was boiling at that point. And that's awesome that they told us that, because we would have had to otherwise figure it out, because 20 plus 82 equals 102, which is 100 is boiling. So as long as the solution is boiling, more heat is only going to cause more boiling. It's not going to raise the temperature. As soon as something reaches boiling temperature, it's just going to keep boiling and stay right around the boiling point. Okay. Adding NaCl no longer increased the reaction rate. Adding more NaCl would decrease. The boiling point was reached, so no further data could be gathered with this procedure. That's right. And since it wouldn't quit boiling until it was all gone, then there wouldn't be any need for us to add more heat because we have nothing to heat. Okay, number 31. Based on the results of experiment 3, one can reasonably conclude that as the amount of NaCl added increased from 0 moles to 0.1 mole, the maximum rise in temperature within 15 minutes of the start of the reaction, what did it do? So as this increased, what happened to this? It just kept increasing. That's it. It increased only. Because it only says to 0.1 mole. So that wouldn't be stayed the same because it didn't stay the same until it got to 0.125 moles. So since we're looking at only up to 0.1 mole, it increased only. 32. If a trial had been done in experiment 3 with 0.60 moles of NaCl added, 0.060 moles. Oh, that's really important. Those O's, 0.060, that would be right here. The maximum temperature increase of the mixture that would have occurred within 15 minutes would have been closest to, so 5, 6, 7, it's going to be more than half of this because this is, because 0.06 is only 1 point difference, and this is 1.5 difference. So the difference in between these two is 16. So maybe about 40-ish. Let's see what we got. 34, no, because that's 0.5, 42, 50 is 0.75, so that's 2. So 42 is the only one that's in between 0.5 and 0.05 and 0.075. Okay, so G. Let's see. 33. Which of the following factors affecting the reaction of milligrams of magnesium and H2O was studied in experiment 1, but not in experiments 2 or 3? Okay, so what did we say was studied in experiment 1? Surface area of magnesium. And that wasn't studied because the magnesium amount and type, powdered and 0.10 moles, stayed the same. So the surface area of magnesium was studied in experiment 1. 34. An engineer is designing an FRH to be used with 100 milliliters of H2O that will most rapidly generate the greatest amount of heat with the least amount of materials. Based on the results of experiments 1, 2, and 3, which of the following specifications should she choose? Okay, so are we looking at magnesium ribbon? Okay, so we're looking at powder, Fe, NaCl, and magnesium powder. So ribbon powder. So magnesium powder generates heat way faster than magnesium ribbon. So we want to get rid of these with magnesium ribbon. So that leaves F and H. And 0.1 NaCl is the same here, and the amount of magnesium is the same. So we want to see iron powder. Which one of these is looking at iron? It's experiment 2. .5 moles, 0.7 moles. Oh, okay, so 0.5 moles and 0.7 moles on here had the same increase. So we want the one with the least amount of material, so that's going to be the 0.5, and that's F. Okay. 35. It has been observed that as magnesium and H2O react, the magnesium hydroxide that is produced forms an unreactive coating on the magnesium surface. Okay, so this right here is a solid, and it starts coating the surface of this magnesium, and that's going to reduce the surface area that's available to the reaction. Which of the following models for why NaCl speeds up the reaction is most consistent with this observation and the results of the experiments? So somehow we want to see maybe this NaCl gets rid of the magnesium hydroxide or takes it off of the magnesium. NaCl absorbs heat, causing the MgOH2 to melt off of the magnesium surface. That couldn't work because if it absorbed heat, the melting is going to be less. NaCl binds with Fe to inhibit the reaction of magnesium with H2O. That doesn't have anything to do with the magnesium hydroxide, so we're not concerned about that. NaCl reacts with magnesium hydroxide to form a stronger barrier against H2O. That's not really going to help the reaction. NaCl reacts with MgOH2, removing the coating from the magnesium, allowing more contact with H2O, and that's going to increase the reaction, which is what we want. We want to know why NaCl would increase the reaction, and we also want it to relate to this magnesium hydroxide. So D is the only one that increases the reaction and relates to the magnesium hydroxide. All right, let's see, we got any more? 35? Nope, that's all. Done. Passage 6.